This video covers Griffiths E&M section 1.4.1 spherical coordinates. So far we've been talking about things in terms of Cartesian coordinates, but depending on the symmetry of your problem, Cartesian coordinates may not be the most appropriate coordinate system to use. One of your other options is going to be spherical coordinates, which is what we'll talk about in this video. Okay, so here's our Cartesian coordinate system, x, y, z. And previously we had discussed, a point in that space, call that point P. It is at coordinates x, y, z. We can draw a vector that points from the center of our coordinate system to that point. Okay, let's call that vector r. I can go ahead and decompose this vector r into the three different components, but first I need to define some angles that are appropriate here. Okay, so I'll first describe the polar angle theta, which is the angle from the positive z-axis to down to my vector r. I will then project my point into the xy plane. So I have this projection right here. That projection right here has a length of r sine theta, because it's essentially this piece up here. And I'll define another angle, which is the distance from the angle from our x-axis, a positive x-axis, to our projection. Call that phi. So we have theta, which is our polar angle, and phi, which is our azimuthal angle. All right. So the first thing we might want to do is be able to describe our previous Cartesian coordinates x, y, z in terms of our new vector and our new angles. Okay, so eventually I'm going to want x, y, and z. I'll start with z because I think it's probably the easier one to do. Z is just going to be this component of my original vector. Right? So I have I can make a triangle with my vector r, my angle theta, and that triangle is going to have two pieces. I drew that a little bit off. I don't want to be too confusing here. That's our triangle right there. And our z is going to be r times cosine of theta. All right, and the reason I wanted to make sure I drew that correct is because this piece right up here, that is r sine theta, which is the same as our projection in the xy plane. Okay. So I have my r sine theta in my xy plane, but I need to project that projection again onto either the x-axis, the y-axis, or the y-axis. All right, so let's do the x-axis. I again have a triangle, this triangle. I know the hypotenuse of my triangle is r sine theta, so I'm going to project that on its adjacent side. So I get r sine theta cosine phi, and then the other side is going to be r sine theta sine phi. There you go. So that's how you get x, y, and z out of that. Now, the next thing that we are going to want to do is be able to build our infinitesimal displacement vector in 3 dimensions. With that, we can then build our infinitesimal area and our infinitesimal volumes. So I have my coordinate system again. I'll draw my vector here, r vector, and that vector, if I were to change it slightly in the r direction, that is my r hat direction. If I change it in the direction of theta, right, so that's kind of down into the xy plane, that is theta hat. And if I wanted to change that vector in the phi hat direction, that's into the page. So my total infinitesimal displacement vector is going to be the components of all of those infinitesimal changes. So I have dl in the r hat direction plus dl theta in the theta hat direction plus dl phi in the phi hat direction. All right, so let's figure out what each of these components are. If I take a vector r and I move a little bit in the r direction, that little change is going to be just a dr. Okay. Now if I have a vector r and I have a new vector down here, how far has that tip traversed? That has gone a distance r d theta. Right, I've rotated by some amount d theta, and now the tip of that vector is now at a distance r d theta away. And then I'll do the third one. I have some vector r. I project that down into my xy plane. That's r sine theta. Now I rotate that vector some amount d phi. Now this distance here becomes r sine theta d phi. Right, so each of these components here are the infinitesimal displacements in that particular direction. So I can write that infinitesimal displacement vector dl as dr in the r hat plus r d theta in the theta hat plus r sine theta d phi in the phi hat. Now, what do I do to build my infinitesimal area vector? Right. Well, there's multiple ways I can combine each of these different components depending on the surface area that I actually care about. So I can't give you an exact answer for what that is, but we can go ahead and use these to build our infinitesimal volume component and use that to calculate the volume of a sphere, which you should know the answer to. Okay, so let me just rewrite this vector that we just created. That is dr in the r hat direction plus r d theta in the theta hat direction plus r sine theta d phi in the phi hat direction. Right, so what is my infinitesimal volume element? Right, I only have one way to do that, and I build that by taking the product of all of these infinitesimal lengths, just like I did in Cartesian coordinates. So that becomes r squared, there's two r's, dr. I'm left with a sine theta d theta, and I'm left with a d phi. Right, so those are all the components there. So if I want to know the volume of a sphere, let's say that has radius r, I'm going to integrate my volume. Okay, so let's do our r bounds first. What are the limits going to be for r if I want to integrate over a sphere of radius r? Okay, I'm going to start at r equals 0, and I'm going to go to r equals capital R, size of my sphere. What are the bounds on theta going to be? Well, theta can take on values from 0 to pi, and phi can take on values from 0 to 2 pi. Right. Okay, then I integrate that infinitesimal element, r squared dr, sine theta, d theta, d phi. Okay, the r squared integral, we can do that, plug in its bounds. That's 1/3 r cubed. Integral of phi, there's no other phi's, so that just becomes an integral over d phi. It's valued at 2 pi and 0. That gives us a 2 pi. And I'm left with the integral from theta equals 0 to pi of sine theta d theta. Do that. That integral becomes 2, and you're left with 4/3 pi r cubed, which you knew was the volume of a sphere. All right, I'm not going to write these down, but we took derivatives of our of functions or vectors in our three-dimensional space using Cartesian coordinates. Those had special names like the gradient, the curl, and the divergence. There are different functional forms for the gradient, the curl, and the divergence, and all other types of second-order derivatives in spherical coordinates, and they're listed in your book. Then you should use the appropriate form of that derivative depending on the coordinate system that you're using.